Good morning, everyone. So today's topic we will discuss about applied numerical method in MATLAB. So this cover are the part 1, which is modeling, computers, and error analysis. So let's proceed. So first, chapter 1, mathematical modeling, numerical methods, and problem solving. So before we discuss it, let me read to you the first objectives. So the primary objectives of this chapter is to provide you with a concrete idea of what numerical methods are and how they are related to engineering and scientific problem solving. So there are specific topics and objectives. So first, learning how mathematical models can be formulated on the basis of scientific principle to stimulate the behavior of a simple physical system. Second, understanding how numerical methods afford a means to generate solution in a manner that can be implemented on a digital computer. Third, understanding the different types of conservation laws that lie beneath the models used in the various engineering disciplines and appreciating the difference between steady state and dynamic solution of this model. Last, learning about the different types of numerical methods that we'll cover in this book. So first, a simple mathematical model. What is simple mathematical model? A mathematical model can be broadly defined as formulation or equation that expresses the essential features of a physical system or process in mathematical terms. So, in a very general sense, it can be represented as a functional relationship of the form which is dependent variable is equals to f times independent variables and parameter enforcing functions, where dependent variable is the characteristic that usually reflects the behavior of a state of the system. Then the independent variable are usually the dimension such as time, space, along with the system behavior is being determined. Next, parameter are the reflective of the system properties or composition. So, lastly, the forcing function are external influences acting upon it. So we have, for example, y is equals to fx. So the dependent variable here is the y and the independent variable is the f. Next, we have conservation laws in engineering and science. There are majors or other majors organizing principles in the science and engineering. Among the most important of these are the conservation law. Although they form the basis for a variety of complicated and powerful mathematical methods, the great conservation laws of science and engineering are conceptually easy to understand. They are boiled down to change is equals to increase minus decrease. This is precisely the format that we employed when using Newton's law to develop a force balance for a bungee jumper. So, although it's simple, it embodies one of the most fundamental ways in which conservation laws are used in engineering and science. That is to predict the changes within the respect of time. So, that will be given a name or a special name, which is the time variable or transient computation rather. So aside from predicting changes, another way in which conservation laws are applied is for cases where change is non-existent. If change is zero, the equation becomes change is equals to zero or equals to increase minus decrease, or increase is equals to decrease. If no changes occur, the increase and the decrease must be balanced. This case, which also given a special name that is the steady state calculation. So next, numerical methods covered in this book. So the part 1 or the part 2 of this is the roots and optimization, where the roots is the solve for the x so that f of x is equals to 0. So optimization is also solve for the x so that f prime x is equals to 0. So part 3, which is linear algebraic equation. Given the a's and the b's, solve for the x's. So we have a sub 11 x sub 1 plus a sub 12 x sub 2. So equals to b sub 1. So a sub 12 plus 6 sub x sub 1 plus a sub 22 x 2 is equals to b sub 2. Next we have part 4, which is the curve fitting, which includes the linear regression and interpolation. Part 5, we have integration and differentiation. So integration is to find the area under the curve, and the differentiation is find the slope over the curve. So part 6 is different equation. So given the dy over the dt is equals to f times x and y. So solve for the y as a function of t. So y sub 1 plus 1 is equals to y sub 1 plus f times t sub 1 and y sub 1 times theta t. So next we have chapter 2, MATLAB Fundamentals. So there is a chapter objectives in this MATLAB Fundamentals. The primary objective of this chapter is to provide an introduction and overview of how MATLAB calculator mode is used to implement interactive computation. There are specific objectives and topics. So first, learning how real and complex numbers are assigned to a variable. Second, learning how vectors and matrices are assigned values using simple assignment, which is the colon operator, the linspace, and the log space function. So next, understanding the priority rules for constructing mathematical expression. Next, gaining a general understanding of built-in function and how you can learn more about them with MATLAB help facilities. Lastly, learning how to use vectors to create a simple line but plot based on equation. In this chapter, we will learn how MATLAB can be used to analyze such data. Beyond showing how MATLAB can be employed to compute quantities like drag coefficient, we will also illustrate how its graphical capabilities provide additional insight into such analysis. So the MATLAB environment. MATLAB is a computer program that provides the user with a convenient environment for performing many types of calculations. It provides a very nice tool to implement numerical methods. The most common way to operate MATLAB is by entering commands and one at a time in the command window. In this chapter, we will use the interactive or calculator mode to introduce you to how common operations such as performing calculations and creating plot. So MATLAB uses three primary windows: the command windows and the graphic windows and the edit windows. So example, we will make use of the command and graphic windows. Note that we will use the edit window to create M files. The command window will open with the command prompt being displayed. So this is the command prompt, the two greater than symbol. So the calculator mode of MATLAB operates in a sequential fashion as you type in the command line by line. For each command, you get the result. So for example, we have command prompt being displayed 55 minus 16, MATLAB will display the results. So answer is equals to 39. So next we have, so notice that MATLAB has automatically assigned the answer to a variable which is ans. So do you see the ans there is automatically it will display the answer which is 39. So next we have assignment. So assignment refers to assigning values to variable names. This results in the storage of the values in the memory location corresponding to the variable name. So under the assignment we have the scalars. The assignment of values to scalar variable is similar to other computer languages. So for example, try typing command prompt A is equals to 4. Note how the assignment echo prints to confirm what you have done. So A is equals to 4. So echo printing sa characters in MATLAB, it can be suppressed by terminating the command line with a semicolon character. So for example, we have try typing command prompt will display. So A is equals to 4 and A is equals to 6 semicolon X is equals to 1 semicolon. So MATLAB treats name in the case sensitive manner. So the result will be A is equals to 4. So MATLAB treats name in the case insensitive manner. So example about the capitalized A and the lowercase a, they are not the same because it's of sensitive manner. So second or number 2, which is array, vectors, and matrix. So an array is a collection of values that are represented by a single variable name. One-dimensional are called vectors and two-dimensional arrays are called matrix. So example, a row vector can be assigned as follows. Command prompt A is equals to bracket 1, 2, 3, and 4, and 5. Remember that brackets are used to enter arrays in the command mode. For example of this, do you see that before the 1 there is a bracket? So the result will display, which is 1, 2, 3, and 4. You will see the difference of the result in the that you command. So a column vectors can be entered in several ways. So we have command prompt B is equals to bracket 2 is to 4 is to 6 is to 8 is to 10 or bracket. So the result will be B is equals to 2, 4, 6, 8, and 10. So example number 2. We have bracket, or did you see the use of bracket? It's very useful in determining what is a kind of arrays that you will use. So example, prompt command A, capital A is equals to bracket 1, 2, 3 semicolon 4, 5, 6 semicolon 7, 8, 9 bracket. So the answer is A is equals to 1, 2, 3, and 4, 5, 6, 7, 8, 9. But the difference is the arrangement. So example number 3. Enter K would be stuck after the 3 and the 6 and to assign the matrix. So the result is A is equals to bracket 1, 2, 3, 4, 5, 6, 7, 8, 9 bracket. So in addition, the enter carriage return can be used to separate the rows. So the colon operator. The colon operator is a powerful tool for creating and manipulating arrays. If a colon is used to separate two numbers, MATLAB generates the numbers between them using an increment 1. So for example, we have command prompt t is equals to 1 is to 5. The result will be t is equals to 1, 2, 3, 4, 5. If the colons are used to separate three numbers, MATLAB generates the number between the first and third number using an increment equal to the second number. So, for example, we have example 1, we have command prompt t is equals to 1 is to 0.5 is to 3. So the result t is equals to 1.0, 1.5, 2.0, 2.5, and 3.0. Note that the negative increments can also be used. For example, number 2. Command prompt t is equals to 10 is to negative 1 is to 5. So the result answer is 10, 9, 8, 7, 6, 5. So aside from creating series of the number, the colon can be used as a wildcard to select the individual rows and the columns of a matrix. When a colon is used in the place of a specific subscript, the colon represents the entire row of column. For example, the second row of matrix A can be selected as A parenthesis 2 is 2 parentheses. So result answer is equals to 4, 5, and 6. So we can also use the colon notation to selectively attract or extract a series of elements from within an array. For example, based on the previous vector that we discussed, so t is equals to t parenthesis 2 is to 4 parentheses. So the result answer is equals to 9, 8, and 7. So next, we have the linspace and logspace functions. The linspace and logspace function provide other handy tools to generate vectors of space points. It has a form of linspace is equals to x1 and x2 and x3. So example, so linspace 0 and 1 and 6. So the result is 0, 0.2, 0.4, 0.6, 0.8, and 1. So if the n is omitted, the function automatically generates 100 points. So the logspace function, this is the linspace function So linspace function generates a row vector of equal space points. It has a form of this. So this is the example and the result. So next we have the logspace function. The logspace function generates a row vector that is logarithmically equally spaced. It has the form of logspace x1, x2, x3. It has the same form with linspace, but the difference is the logspace and the linspace word. So it use lin, it is use log. So for example, command prompt logspace equal to -1 plus -1, 2, and 4. So the result is answer is equal to 0.1, 1, 10, and 100. If n is omitted, it automatically generates 50 points, while the linspace, it generates 100 points. So next we have the mathematical operations. So operations with scalar quantities are handled in a straightforward manner, similar to other computer languages. The common operators in order or of priority are: first, we all know the exponential or the exponentiation, the negation, next is the multiplication and division, next left division, squared, and plus and minus, which is additional and subtraction. So this operation will work in calculator fashion. So try command prompt 2 times pi. So we all know the pi value is 3.1416. So the answer is 6.2832. So if you command or you try to type the 2 times pi, the answer that's shown in the MATLAB is 6.2832. Next, also scalar real variables can be included. Command prompt y is equals to pi divided by 4. So y raised to negative 2.45. The answer is 0.5533. So 5,533. 0.5533. Result of calculation can be assigned to a variable as in the next to last example, or simply display as in the last example. So number 4, use of built-in function. MATLAB and its toolbox have rich collection of built-in function. You can use online help to find out more about them. So example, we have try typing command prompt help log natural logarithm. The result will be log x is the natural logarithm of the element of the x. So complex result are produced if x is not positive. See also log 2, log 10, exp, and log m. One of their most important properties of MATLAB's built-in function is that they will operate directly on vector and matrix quantities. So for example, we have log A, answer is 0.0639110,986. 1.3863, 1.6094, 1.7918, and 1.9459, 2.0794 to 1.197. So, and you will see the natural logarithm function is applied in array style, elements by element to the matrix A. Most functions such as square root, absolute, sin, a cosine, tangent, and exp are operate in array fashion. So certain functions such as exponential and square root have matrix definition also. So next we have the graphics. MATLABs allow graphs to be created quickly and convenient. For example, to create a plot, we have to try to type command prompt plot parentheses t and v parentheses. So The graph appears in the graphics window and can be printed or transferred via cupboard or to other programs. So this is the result. As you see, if you try to plot this, the result will be this. So you can customize the graph a bit with the commands such as the following. So the title or plot of V versus T, X label, which is the value of T, and Y label, which is the value of V. So, and grid. So as you see, this is an example of plot of V versus T, or the title. So there are specific colors and symbol and line types. So this is the example of colors, and this is the symbols and line types. You can use that in your what you call it, graph, to have a customize or design to emphasize the data that you put or you command. So now we will move on to the chapter 3 of the book. This chapter 3 is also included in part 1. So there is a chapter 4 after this. So chapter 3, the programming with MATLAB. M files. The most common way to operate MATLAB is by entering commands one at a time in the command window. M files provide an alternative way of performing operations that greatly expand MATLAB problem-solving capabilities. First, let me tell you about about the M files. An M file contains a series of statements that can be run all at once. Note that the nomenclature M file comes from the fact that such files are stored with a M extension. M files come into flavored script files. This is the script file and the function file. So script file. When we say script file, a script file is merely a series of word. That is MATLAB. So MATLAB command that are saved on file. They are used for retaining a series of commands that you want to execute or on more than one occasion. So don't bother with the MMLab, it's MATLAB. So the script can be executed by typing the file name in the command window or by invoking the menu selection in the edit window. So debug, try to find the debug and run. So example of script file. We have a problem. Develop a script file to compute the velocity of the free-falling bungee jumper. So the solution, open the editor with the menu selection, File, New, and File. Type in the following statements to compute the velocity of the free-falling bungee jumper at a specific time. Next, we have G is equals to 9.81, which is the gravity. Then M is equals to 68, T is equals to 12, and CD is 0.25. And the V is equal to square root of G times M over CD times tangent times G times CD over M times T. So this one is the formula, and this one is the given in the book or in the problem. So save the file as the script demo M and return to command type and type script demo. So the result will display as V is equals to 50.6175. Thus, the script executes just as if you had to type each of its lines in the command window. So, we have 3.2, which is another flavor of the M files, which is function files. So, function files are M files that start with the word function. It contrasts to script files. Yes, it is. They can accept input, arguments, and return outputs. Hence, they are analogous to use-defined function in programming languages such as Fortran, Visual Basic, or C. So, the syntax for the function file can be represented generally as function outvar is equals to func name, parentheses arglist, parentheses. So, help comment statement outvar is equals to value. So, where outvar is the name of the output variable, the func name is the function name, arglist is the function argument list, help comments is the text that provide the user with the information regarding to function. And statement is MATLAB statements that compute the value that is assigned to outvar. So, for example, the problem statement is compute the velocity of free-falling bungee jumper. But now, we will use a function file for the task, for this task. So, as you see, we use the script file, but now, we will use the function file with the same problem. So, the solution, function v is equals to freefall val times t, m, and cd. So, freefall val is bungee velocity with second order drag. So, v is equals to freefall times t, m, cd, computer the free falling velocity of an object with a second order drag. So, input, t is equals to time, which is the unit of time is s or seconds, m is mass, which is have a unit which is kilogram, cd is the second order drag coefficient, which have the unit is kilogram per meter, and output is v is equals to downward velocity, which is have a unit which is meter per seconds, and also the constant gravity, which is 9.81, or the acceleration gravity. So v is the square root times g times m over cd times tangent times square root of times g times cd over m times t. So, save the file as the freefall val. To invoke the function, return to the command window and type in freefall val 1268.1 and 0.25. So, the result will display as answer is equals to 50.61.75. So, as you see, in script files and function files has the same outcome, which is 50.6175, but different equation and solution. So, next we have subfunction. When we say subfunction, functions that can call out other functions. Although such functions can exist as separate M files, they may also be contained in single M file. So, for example, function v is equals to freefall subfunction times t and m and cd. So, v is equals to velocity times t times m cd. So, function v is equals to val times t M, and C, D. So G is the 9.81. This is a constant given. So the formula is V is equal to the square root of G times M over CD times tangent times square root of G times CD divided by M times D. So type N. If we run free false subfunction from the command window, the result is identical to example. So free false subfunction 1268.1 and 0.25. Answer is 50.61 and 65. However, if we attempt to run the subfunction val, an error message occurs. Val times 12, which is 1268.1 and 0.25. The result or the message occurs undefined command or function val. As in section 3.1, information is passed into the function via the argument list and is output via the function name. So two other functions provides way to enter and display information directly using the command window. So we have the input function. This function allows you to prompt the user for values directly from the command window. So its syntax is N is equals to input or prompt string. So for example, M is equals to input of mass. When the line is executed, the user is prompted with the message mass or kilogram is. If the user enters a value, it will be assigned to a variable M. So the input function can also return user input as a string. To do this, an S is appended to function argument list. For example, name is equals to input, then enter your name, then S. This function provides a handy way to display a value. Its syntax is display value or dips value, where the value would like to display. So we have table 3.1, the commonly used formal and control codes employed with the fprint functions. So format code D, which is description is the integer format. E is a scientific format with the lowercase e. Big letter E is the scientific format with the uppercase E. F is the decimal format. G is the more compact of E or F. Control code is N, which is start new line. T is the tab. So the fprint function. This function provides additional control over the display of information. A simple representation of its syntax is fprintf parentheses format x. So where format is a string specifying how you want the value of the variable x is to display. So a simple example will be to display a value along a message. For instance, suppose that a variable velocity has a value of negative 50.6175 to display the value using 8 digits with 4 digits to the right of the decimal point along with the message. The statement along with the resulting output will be fprintf. The velocity is 8.4 f meter per second and velocity. So the velocity is 50.6175 meter per second. So creating and accessing files. MATLAB has the capability to both read and write data files. The simplest approach involves a special type of binary file called a mat file, which is expressly designed for implementation with MATLAB. Such files are created and accessed with the save and loads command. The save command can be used to generate a math file holding either the entire workspace or a few selected variables. An example is the representation of its syntax. Is save file name var1, var2 to variables. So, which retrieves the variables var1 through var from the file math. So, next we have the structure programming. When we say structure programming, the simplest of all files perform instruction sequentially. That is, the program statements are executed line by line, starting at the top of the function and moving down to the end. So, because a strict sequence is highly limiting, all computers' languages include statements allowing program to take non-sequential paths. This can be classified as decision or selection and loops or repetition. Decision is the branching of T-loop based on a decision, and loops or repetition, the looping of flows to allow statement to be repeat. So 3.1 we have decision. The F structure. This structure allows you to execute a set of statements if a logical condition is true. Its general syntax is if condition statements end, where condition is a logical expression that is either true or false. So, example, function grader grade. So, grader or grade is determines whether grade is passing. So, input grade is equals to numerical value of grade, which is 0 to 100, then output display a message if grade is less than negative 60. So, greater equals 60. So, this passing grade, so end. So, the following illustrate the result of grader is 95.6, which is the passing grade. So, the FL structure. It often happens that the false option of an if-else structure is another decision. This type of structure often occurs when we have more than two options for a particular problem setting. For such case, a special form of decision structure that if has been developed. It has the general syntax if condition sub 1 statement sub 1 else if condition sub 2 statement sub 2 else if condition sub 3 statement sub 3 and else statement else end. So next we have the switch structure. The switch structure is similar in spirit to the if-else structure. However, rather than testing individual conditions, the branching is based on the value of a single test expression. Depending on its value, like different blocks of code are implemented. So in addition, an optional block is implemented if expression takes on none of the prescribed values. It has general syntax, which is switch, text expression, case value sub 1, statement sub 1, case value sub 2, statement sub 2, to otherwise statement, otherwise end. So next we have loops. Loops perform operation repetitively. There are two types of loops depending how the repetition are terminated. A, for loops end after specified number of repetition. A while loop ends on the basis of a logical condition. So, the for end structure. A or loop repeats statements a specific number of times. In general syntax is for index, colon, starts, colon, step to finish. So, statement end. So, example, for I is equals to 1 is to 5. So, the display I, the end result will be 1, 2, 3, 4, 5. So another example is for j is equals to 10 is to negative 1 is to 1. So the display j, and the result will be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Next, we have the while structure. A while loops repeat as long as a logical condition is true. Its general syntax is while condition statement ends. So example, x is equal to 8. While x is greater 8, x is equal to x minus 3, display x. So the result is x is equal to 8, 5, 2, negative 1. So, now 3.4, nesting and indentation. So nesting refers to placing structure within other structure. So problem statement, we have example this. The roots of quadratic equation. So f of x is equal to ax squared plus bx plus c. So can be determined with the quadratic formula, which is x negative b plus minus square root of b squared minus 4ac over 2a. So function quadroots is quadroot a, b, c. The quadroots or roots of quadratic equation. So quadroots a, b, c is the real complex roots of quadratic equation. Input a is equals to second order coefficient, b is equals to first order coefficient, c is zero order coefficient. So the output r1 is the real part of the first root, I1 is the imaginary part of the first root, R2 is the real part of second root, I2 is the imaginary part of second root. So if A is equals to 0, special cases else, so quadratic end. So passing function to M file. So anonymous function allows you to create simple function with creating an M file. They can be defined within a command window with the following syntax. So fhandle is equals to @arglist or argument list expression. For example, f of 1 is equals to x and y, x squared plus y squared, semicolon. So the result is f1, which is 3 and 4. So the answer is 25. So functions. So functions are the functions that operates on the other function which are passed to it as input arguments. The function that is passed to the function is referred to as a pass function. A simple example is the built-in function fplot, which plot the graphs of function which it has a syntax which fplot, fun, and limbs. So, example, val is equals at t. So, square root 9.81 times 68.1 over 0.25 times tangent square root of 9.81 times 0.25 over 6.81 times t. We can then generate a plot from t is equal to 0 to 12 as fplot val is equal to 0 to 12. So this is the result.
Chapter 4, Roundoff Error and Truncation Error. We have our chapter objectives. The primary objective of this chapter is to acquaint you with the major source of error involved in numerical methods. Specific objectives and topics covered are: first, understanding the distinction between accuracy and precision. Second, learning how to quantity error. Third, learning how error estimate can be used to decide when to terminate an iterative calculation. Fourth, understanding how roundoff errors occur because digital computers have a limited ability to represent numbers. Lastly, understanding why floating point numbers have limit on their range and precision. Accuracy and precision. Accuracy refers to how closely a computed or measured values agree with the true value. Precision refers to how closely individual computed or measured values agree with such other. An example of marksmanship illustrating the concept of accuracy and precision. This sample A is an inaccurate and imprecise. Then B is accurate and precise. C is inaccurate and precise. Then D is accurate and precise. So this is the simple illustrating about in accuracy and precision. Next is numerical error arises from the use of approximation to represent exact mathematical operation and quantities. For such error, the relationship between the exact or true result and the approximation can be formulated as true value is equals approximation plus error. The numerical error is equals to discrepancy between the truth and the approximation. E1 is equals true value minus approximation. Then next is round-off error. Round-off error created due to approximate representation of numbers. Round-off error arises because digital computer cannot represent some quantities exactly. Okay, there are two major phases of round-off errors involved in numerical calculation. First, digital computers have size and precision limit on their ability to represent numbers. Second, certain numerical manipulations are highly sensitive to round-off error. This can result from both mathematical consideration as well as from the way in which computers perform arithmetic operation. Um, I have some example here, but hindi ko na-include sa PowerPoint. So, babasahin ko na lang ang aking example. If you have a number like 1 divided by 3 and you had 6 significant digital computation, so 1 divided by 3 approximated as 0.33333. So there are 6 trees, and then that is how to that is a simple example that I searched in round-off error. Next is truncation error. Truncation error are those that result from using an approximation in place of an exact mathematical procedure. From example, we approximated the derivative of velocity of a bungee jumper by a finite difference equation of the form. So this is the formula that that we include in the PowerPoint. dv all over dt approximated delta b all over delta t is equals to b times t1 plus 1 minus b times t1 all over t1 plus 1 minus t1. So, excuse me, this is the formula or total number error. The total number error is the summation of the truncation and roundoff error. In general, the only way to minimize roundoff error is to increase the number of significant figures of the computers. Further, we have noted that roundoff errors may increase due to subtractive cancellation or due to an increase in the number of computation in an analysis. Okay. Blunders, model errors, and data uncertainty. Blunders. Blunders can occur at any stage of mathematical modeling process and can contribute to all the other components of error. Blunders are usually disregarded in discussion of numerical methods. Then next is model error. Model error relates to bias that can be ascribed to incomplete mathematical models. Data uncertainty is errors sometimes enter into an analysis because of uncertainty in the physical data of which a model is basis. So that's all.